All right, so this is what we're dealing with, right? We have the actual box itself. It has some weight to it, so the cables are going to experience they're going to experience some tension. So you got one, two, three, four cables, kind of pushing because the weight is pushing down, so that means the tension just goes in the opposite direction, right? But don't worry. At the end of the day, it doesn't matter what you assume; it just kind of works itself out. Then they're also saying there's an applied force to pick up the actual assembly plus a beam, BAC. Um, that doesn't come to the very end. And you might think like, okay, you have a force going up, so that means tension's going in the opposite direction. But that's not true. It's kind of like a local system that you have to look at the box itself. And all this, I mean, it doesn't matter. Like I said, you might think that the tension's in the opposite direction, but no, it's kind of like if you're picking up the entire assembly, this cable's still going to be in tension because of this weight, if that makes sense. So, first step, for all these problems, free body diagram. So right now, I like to get the angle first, which is what I did here. So what I like to do is I like to look, obviously they give us dimensions, right? They give us a distance here, a height here, and so it's gonna have some length to it, but let's see what we could do with it. They give us 1.25 meters from here to here, and here to here. So the whole system's like equally, equidistant, if it's the right term, right? It's all like perfectly symmetrical, okay? So, and as you can imagine, right, just thinking of it logically, if you were to pick it up, this system's not going to move, right? You're just going to pick it up straight up and it's going to be in equilibrium. So again, I like to get my angles first because I already see that this is at an angle. So I don't like dealing with like triangles. And I'm sure you see it a lot in statics, like 3, 4, 5, 5, 12, 13 triangles, all these other types of triangles, right? So in this case, I'm looking into the negative x direction, which is going this way. I'm looking at this box right here. Boom, 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 right? I see these two cables are pushing up, which is what you see here if you see the little arrows. And then obviously there's an angle here and an angle here. And they're the same angle, obviously, right? Because it's 1.5 meters from here to here, 1.5 meters from here to here, and then 2 meters high. And if you see it, right, just multiply these two by 2 and you'll see it's a 3, 4, 5 triangle. So this is 3, this is 4, and this is 5. This is 3, 4, and 5. So nothing crazy about that. I like to work with thetas. I don't like doing those fractions that you see in solutions, things like that, or maybe your professor does it, but I like to go straight to the angles, find the theta. So just do basic trigonometry. You could have done cosine of 3 over 5 or sine of 4 over 5, which is what I did. Sine theta of 4 over 5 is equal to 0.8. Take the inverse to get theta, you get 53.13. Make sure your calculator's in degrees to get that, not radians, okay? So once you have that, the next step is to, I do more free body diagrams, okay? So check this out. So I do a free body diagram in the x direction. So now I want, what I like to do sometimes is, in this specific problem, I like to do it, right? But I mean, it all depends on the problem. But in this one, it was, so I can explain it to you guys, I like to put everything in the direction of x, okay? So now we're looking at everything here. So in this case, I'm looking at this cross section, okay, into the page that way. And that's that square that you see there. So if you're looking at it from this way onto this surface, you're going to see this arrow pointing up and this arrow pointing up. You can't see that back arrow, but it's there, right? So if you do that, you have T going up, okay? And this T going up, right? You can kind of imagine it. And it has some component to it. In this case, I just put T. But it's actually this upper component, which is T sine theta of this angle, okay? But in this case, it doesn't even matter. Just look at it logically. Whatever's here is also here, right? So it's equal and opposite kind of thing. And even then, you don't even need it, right? Because we're doing some of the forces in the x direction. But I'm just trying to kind of get you to see it visually. But and then you also have the weight of the box itself going down. This force, we don't care about it right now. You might see this, you might want to throw it in there. And it's not going to affect your answer for this specific case, right? Because we're doing it in the x direction. But it's still not there right now. That's at the very end of the problem. I mean, that's just the force required to lift the assembly. Okay, it's not part of the free body diagram local to the box, okay? So in this case, you have that, okay? If we go to the next one, now let's do free body diagram in the y. If you do a free body diagram in the y direction, so I want everything in the y direction, right? Just like I did here. So now I'm gonna look at it just like I did in this case. I'm gonna look at this surface, okay? Now I have this tension here and this tension here. That's the magnitude of tension, so these are right. This should have been a T whatever sine theta, but it doesn't even matter because we were doing it in the x direction. But in this case, this really is T, okay? So we're looking at these two arrows right here, and then you also have weight coming down, but y is in this direction. So we have this positive component, right? It's positive because look, the tension is coming this way. I'm looking at this arrow, and it's in the positive y direction. Look at y, it's coming this way. So it's in the positive y. And this one's in the negative y, right? It's going in the opposite direction as this one. Now, we already found these angles at theta. That's what we found here. And we know from, you know, triangle geometry from high school that, I forgot what the exact, kind of like a complementary angles or something like that. But point is, this angle is this angle, okay? And it kind of makes sense, right? Because this right here, if you draw a straight line down, this is a right angle. And this angle here, I mean, this triangle, what I'm saying, this triangle is just the flipped inverse of this triangle. So this angle is this angle is this angle, and that right angle is over here. Boom, 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 okay? But point is, now you want to do this. The reason I'm doing this is because I'm going to do some of the forces in the x, some of the forces in the y, and then as you can imagine, some of the forces in the z, okay? So again, I just drew the setup right now. Just hold on to it. And now let's do it in the z direction. So this one was a little bit trickier because you kind of have to see it, and I hope I don't confuse you guys with it, but kind of tilt your paper. Right now we're looking at this same triangle here, this same box, this view with the positive z. In this case it's going up, but in our case it's going to the side. So these two vectors are here, okay? The angle we already determined, right? It was this angle here, which is this one, and then this one. And then you have the weight coming down, right? Or in this case, in the negative z direction. This, like I said, this one's the most confusing, but again, I had to kind of like visualize it for you guys. This was the simplest I could think of at the time, and I'm just kind of explaining it. But you have a negative w, and then two positive tension z coordinates, okay? Z components. And if you start doing the summation of forces in the x, let's start with this one. Again, I just drew the outline. Now let's do the actual summation of forces. Well, there's nothing going on in the x, right? So everything's perfectly up and down. See, that's why I said these don't even matter. So some of the forces in the x direction is 0. Boom. Force in the x is 0. Okay? Do forces in the y now. Some of the forces in the y direction, again, it's in, this is the positive y coming to the right. So you have t cosine theta, right? Because you got to get this component. So it's cosine theta is adjacent over hypotenuse, t. Move t to the other side, you get t cosine theta. And there's two of them, right? You got this one, and then you also have that one in the back. Because remember, we're looking at it in this direction. We're looking at this surface here, okay? So that means there's one right behind it. You can't see it, but it's right behind it. And then this one, same thing with this one. You have this one and this one. So that's right behind this vector, there's another vector, okay? So in this case, we have t cosine theta, but two of them. So we have t 2 t cosine theta. Then you have negative, because it's in the negative y direction, t cosine theta, same thing, right? Cosine theta is adjacent over hypotenuse, so t cosine theta. And you have two of them. And yeah, when they both go to 0, so that means some of the forces in the y direction are equal to 0. So easy. Now let's do some of the forces in the z, okay? You have negative w, bring it down. You have a 2t cosine theta. Again, remember, we're looking at this same box, right? This box here, and we're looking at this component and this component. But remember, there's also this one and this one. So there's two. There's one right behind this one, you can't see it, and there's one right behind this one, you can't see it, okay? But they're the same, so you just multiply by 2, just like we did here. So you'll have, it's a positive, it's going in the positive z direction. So it's, and you can choose whichever angle you want, right? I kind of just drew them, but in this case, you can use we're gonna use sine theta. So sine theta is opposite over hypotenuse. So that means t sine theta is equal to opposite, right? The z component is what we want, so that's the opposite. That's what when you hear me say opposite, that's what I mean. So t sine theta, and there's two of them. So you have plus 2t sine theta. But you also have this one, and it's also a sine theta, right? Sine theta is equal to opposite this component over t, hypotenuse. And there's two of them, this one and this one. So that means another 2t sine theta. So you get w for t sine theta. Now, if you go, well, actually, before I continue, let me show you, this problem wasn't asking for it, but it's like, approach these problems as if you were supposed to find all 6 unknowns, okay? Force in the x, y, z, moment about x, y, z, okay? Always approach these problems in that manner and you'll be all right. So I did it, and as you can see, they get 0, but let me kind of explain why that's the case. So let's do some of the moment about the y-axis. So the y-axis is this black pen, right? It's in this direction. So anything that kind of makes it rotate in any direction about this axis is going to cause a moment about y, right? So in this case, look, this tension, this vector right here, this tension, is going to produce a clockwise moment about y. You can see it, right? It kind of goes this way about y. Look at y. This one also goes up, and it's also going to produce a clockwise moment. So these are 2 negative moments. But what about these? These are going in the upwards direction, right? So it's going around y in the counterclockwise. And so is this one, counterclockwise. So when you do that, check it out. Let's look at, I forgot in what order I did them. But in this case, I did t. Okay, I want the vertical component because that's the one that produces the one in the y direction, which is this one, right? Look at this vector, my bad, I'm going too fast. Look at this shaded vector. It has 2 components. It has the y component, right? And it's y because it runs along the y-axis, and it has a z component because it goes along the z-axis. Anything that's going along the axis of choice, in this case the y-axis, it's never going to produce a moment, okay? It's going in that direction, so it's never going to do it. So in this case, remember, this was theta. Damn, the wind is strong. This was theta, okay? So this component here is t sine theta, the upwards component. And that's going to produce a negative because it's clockwise. It's going to produce a negative component, so it's t sine theta times your distance, 1.25. But guess what? There's 2 of them. So it's 2t sine theta, right? This vector as well, same logic. Do it on your own, kind of think through it a second. And it's 2 of them, so it's 2t sine theta times 1.25. And that's the one you see here, the negative, because it's producing a clockwise. Now, let's say if you look at these right here, this one's same thing, right? It's the z component that you're looking for, and this is the theta. So you want t sine theta times 1.25. And that's a positive t sine theta because it's going to produce a counterclockwise about y. And there's 2 of them, right? This vector and this vector, same logic applies to this one. You want the z component, which is t sine theta. So you'll have 2t sine theta positive times 1.25. Boom, they'll cancel out. There is 0 moment about y, okay? And do the same logic for all of them. Now, some of the, about x, right? This is the x component, so anything that spins it this way. In this case, you'll have the z component. No, the z component, it would have normally, but it's going right through x. There's no distance, right? It's right at the center. So, and you might think, well, isn't it technically acting here? So you're actually 1.5 meters away from x. No, that's not how it works. Usually a good way to remember it is look at the vector, the head. If you break this vector up into 2 components, both of those vectors, it's going to act at that point, okay? So in other words, you have the other one here and the other one here, okay? So use that logic. In this case, now we want the x component of that vector, right? So you want, which is this one right here, I'm sorry. This one is going to produce a clockwise moment about x. And this is where it kind of gets a little crazy if you can see it. Look at x. It's in the positive x like this. Look at the pen. This is the positive x direction, okay? This one is acting, look at this point to B, okay? This is the blue vector. That's going to create a clockwise moment. I mean, you probably can't see it based on the video, but it's going to create a clockwise moment about x, okay? That's acting 2 meters away. And this one and this vector are doing that, okay? They both have the x component, which is t cosine theta, right? You want the cosine theta of the angle. And it's actually acting here. Again, it's not acting here, so you might think, oh, it's not producing a moment. Remember, the rule of thumb is, if you break this vector up into two components, it's both acting at the, going straight to the head, okay? And that's how you know. So 2 meters, t cosine theta times 2 meters, but then there's two of them, so it's 2t cosine theta times 2 meters, and then it's a negative because it's clockwise. So it's negative 2t cosine theta times 2 meters, and that is what you see here, okay? That one right there. Then this is the same, except it is the same, except it's just the opposite now, okay? Now this vector here is the component producing a moment about x. So this is your pen, right? This is the x component coming out. And look at the pencil. It's producing a counterclockwise moment about x, okay? So that's why, again, same logic, there's two of them, so you'll have 2t cosine theta. It's counterclockwise, so it's positive, and then you're at a distance 2. So that's what you see here. And then these mx and my's, you just assume there's whatever this is equal to, that's going to be equal to that. In this case, it's just 0. So you're good. So these two check off. Boom. Sum of the moment about z. Okay, same thing, right? Now anything that kind of just makes it rotate about the z-axis. In this case, it was not this component. Remember, it's going along the positive z direction, so that's never going to make a moment. Okay, no matter where it's at, no matter how far you are from z, it doesn't matter. It's going in the same direction as z, so it'll never make a moment. But, and that's the t sine theta, remember? But t cosine theta, this one is acting 1.25 meters away, and it wants to rotate it counterclockwise because he's coming out. So this one counterclockwise, right? It's going this way. So this one, this component here, and this component in the back want to make a counterclockwise. So it's 2t cosine theta times 1.25. And that's what you see here. And then, but then these two vectors here are counteracting it, right? And that's just a negative 2t. It's the same logic as the other ones, okay? But again, it's the x component, and it's acting 1.25 meters away from z. But this one's doing it clockwise, so that means that these are negative. They just assume a reaction of z for moment, but you find out that mz is just 0 because these two cancel out, these two cancel out, these two cancel out. And it makes sense, right? At the end of the day, you got to think of it logically. If you're picking this up, this thing's not going to want to rotate about an axis in any direction, right? This box is just going to stay perfectly still. You're just going to pick it up and boom. That's it. So now the last step, using this relationship, we found 5 of them, right? The goal is to find all 6, fx, fy, fz, my, mx, mz, all 6 of them. So we already found 5, so we're good. Now let's just focus on step 7, right? They want us to find the tension in the rope. So we know the weight of the box. They kind of give it to us, right? It's the mass is 600 multiplied by gravity, 9.81, and that's what you get here, okay? The weight is 5,886 newtons, okay? So now that you have that weight, I'm just going to go ahead and show you everything, okay? So now that you have that weight, you could find tension because you already found W. So use this relationship and you'll find tension, okay? And then that's it. That's the answer. So now you find out how much tension is in each rope. Now, it's also asking how much force is required if you got to pick up the beam as well. So that's easy. It's just force is equal to the weight. And the tensions are not relevant in this case, right? You're just concerned with the actual weight. The tensions are, they help, right? They're important. They're picking up the box, but they're not important in analyzing the entire system. This force has to pick up the beam itself, BAC, plus the weight of the box. Well, BAC was 30 times 9.81, that's the weight. And then 600 times 9.81, that's the weight of the mass of the block or whatever the thing is. And then that's the force required. And there you go. Easy money. Hopefully that made sense. Let me know if it did or didn't. I'll answer some questions. We'll go from there. Cool, thank you.